The Asynchronous Advantage Actor-Critic, A3C, is a reinforcement learning algorithm that combines parallel agent training with an actor-critic architecture to achieve efficient policy optimization. Let's explore it in 6 parts. The Asynchronous Advantage Actor-Critic architecture. How does A3C handle asynchronous updates from multiple agents? How does the asynchronous update process in A3C improve training stability? How does A3C handle the trade-off between local exploration and global convergence? What are the main differences between A3C and A2C? How does the actor-critic architecture improve learning in A3C? Now, let's explore how the Asynchronous Advantage Actor-Critic architecture achieves this. It improves learning efficiency by combining 2 key ideas: asynchronous learning and the actor-critic method. The first, the core components of A3C. 1. Actor-critic architecture. For the actor, policy network. This part of the model decides what action the agent should take in a given state. Think of it as the decision maker. Instead of picking a single action, it outputs a probability distribution over possible actions. For the critic, value network. This part evaluates how good a particular state is. It helps the actor make better decisions by estimating future rewards. 2. Asynchronous learning. Instead of training a single agent, A3C uses multiple agents running in parallel. Each agent interacts with its own version of the environment, collecting experiences independently. These agents then update a shared global network at different times, making the learning process more efficient and allowing for better exploration of the environment. 3. Advantage learning. The advantage in A3C refers to how much better an action is compared to the expected outcome. This helps the agent focus on useful actions rather than just random exploration. The second, how A3C works. 1. Starting the training process. A global network is created, which serves as the main model. Each agent gets a local copy of this network to work with. 2. The agent's workflow. Get the latest model parameters from the global network. Interact with the environment for a set number of steps, collecting experience. Compute losses using the data collected, policy loss for decision-making and value loss for state evaluation. Calculate gradients based on these losses. Update the global network with these gradients. Repeat the process as agents continue to explore and learn. The third, why is A3C useful? 1. Faster learning. Multiple agents working in parallel explore more efficiently, speeding up training. 2. Scalability. It works well on multiple machines, making it suitable for large-scale tasks. 3. Real-world applications. A3C has been applied in video games like Atari and Doom, robotics, and even traffic control systems. In summary, by using these ideas, A3C has significantly improved how reinforcement learning agents learn and make decisions. A3C is designed to make reinforcement learning more efficient by using multiple agents that learn in parallel. Instead of having a single agent interact with the environment, A3C allows several agents to run independently, each collecting its own experiences. These agents then update a shared global network at different times, which speeds up learning and improves exploration. Let's go step by step to understand how this works. The first, parallel exploration. Think of A3C like a team of explorers, each going into different parts of a new world. Instead of one person slowly mapping out the area, many agents explore simultaneously. Each agent interacts with its own copy of the environment, meaning they can collect different experiences independently. Since each agent explores different paths, we get a more diverse set of experiences. This prevents the model from getting stuck in one type of behavior and makes learning more stable. The second, local network updates. Each agent gathers experiences over a certain number of steps, or until it reaches a terminal state, for example, finishing a game level. Once an agent has enough data, it calculates gradients, which determine how much to adjust the model, for both the policy, decision-making, and value, state evaluation, networks. The third, asynchronous updates to the global network. All agents contribute to a single global network, which acts as the central brain of the system. Unlike traditional reinforcement learning methods where updates happen in sync, A3C allows each agent to update the global network as soon as it has new data. This means updates are happening at different times, reducing the risk of agents making similar mistakes. Once an agent updates the global network, it resets its local copy to match the latest global parameters. This way, every agent benefits from what others have learned. The fourth. Why asynchronous updates work well. 1. Better exploration. Since agents explore in different directions at the same time, they discover better strategies more quickly. 2. More stable learning. Updating at different times prevents agents from reinforcing the same bad habits. This makes training more robust compared to methods that update everything at once. 3. Efficient use of resources. Unlike other reinforcement learning approaches that need large memory storage, like DQN's replay buffer, A3C doesn't store past experiences. This makes it more efficient for real-time learning. The fifth. Challenges to consider. Since agents are updating at different times, some might be using outdated information, which can create inconsistencies in learning. Choosing how often agents update the global network and how many agents to use is key to getting the best results with A3C. In summary, by balancing these benefits and challenges, A3C makes reinforcement learning faster, more scalable, and more effective in complex environments. A3C's asynchronous update process helps make training more stable by using multiple agents that update at different times, leading to better exploration and less correlation between updates. Let's go through the key reasons why this works so well. The first. Breaking correlations between updates. In many reinforcement learning methods, updates happen in a synchronized manner, which can lead to patterns that reinforce bad behaviors or create instability. A3C's agents update the global model asynchronously, meaning they don't all update at the same time. Because updates happen independently, it reduces the risk of harmful correlations that could slow down or destabilize learning. The second. Diverse exploration through parallel agents. If an agent keeps exploring the same areas repeatedly, it might get stuck in a suboptimal strategy. Since multiple agents are exploring in parallel, they gather a wide variety of experiences. This diverse experience set makes learning more robust and prevents agents from getting stuck in bad behaviors. The third. Using the advantage function for stability. The advantage function helps the model focus on actions that are better than average. Instead of blindly following rewards, it measures how much better an action is compared to what was expected. By updating policies based on the advantage function, A3C reduces the randomness, variance in updates, making training smoother and more consistent. The fourth. Efficient use of resources. Some reinforcement learning methods, like DQN, require a huge memory buffer to store past experiences, which can slow down training. A3C doesn't need to store past experiences because its agents are always collecting new data in real time. This makes it more memory efficient and avoids problems related to using outdated experiences. The fifth. Gradual and stable updates. Instead of updating the global model after every action, A3C agents collect gradients over several steps before making an update. Accumulating gradients prevents the model from overreacting to single actions, smoothing out learning and making updates more stable. In summary, by combining asynchronous updates, parallel exploration, advantage-based learning, and efficient resource use, A3C creates a more stable and scalable reinforcement learning process. This allows it to train effectively on complex problems without many of the instability issues that other approaches face. In reinforcement learning, there's always a trade-off between exploring the environment and converging to a good global policy. A3C addresses this challenge through several key strategies. The first. Parallel exploration. A3C uses multiple agents that explore the environment simultaneously. This parallel exploration leads to a broader range of experiences, meaning the agents can discover different parts of the state action space. This helps avoid getting stuck in suboptimal solutions and ensures more thorough exploration. The second. Asynchronous updates. Each agent updates the global model independently, meaning they don't have to wait for each other. This asynchronous approach reduces the risk of harmful correlations between agents' updates, helping stabilize the training process. The agents can keep learning and exploring on their own while contributing to the global model. The third, advantage function. A3C uses the advantage function to focus on improving the policy. This function evaluates how much better an action is compared to the average action in a given state. By guiding updates towards better than average actions, A3C balances exploration, trying new actions, with exploitation, choosing the best known actions. The fourth, entropy, regularization. To ensure the agent doesn't become overly fixated on exploiting a few actions, A3C adds an entropy regularization term to the policy loss. This encourages the agent to keep exploring different actions by maintaining a higher level of entropy in the policy. In this way, A3C prevents the agent from prematurely converging to a suboptimal solution. The fifth, global convergence. Even though each agent explores independently, they all contribute to a shared global model. This global model aggregates the collective experiences from all agents, ensuring that the system converges towards a more optimal and well-rounded solution. The shared model acts as a central hub, pulling together local knowledge to guide global convergence. In summary, A3C effectively handles the trade-off between local exploration and global convergence. By combining parallel exploration, asynchronous updates, focused policy updates, and entropy regularization, it encourages agents to explore the environment thoroughly while ensuring they learn and converge towards optimal strategies. A3C, Asynchronous Advantage Actor-Critic, and A2C, Advantage Actor-Critic, are both reinforcement learning algorithms, but they differ significantly in their update mechanisms and architecture. Let's break down these differences. The first, update mechanism. In A3C, multiple agents interact with different copies of the environment in parallel and update the global model asynchronously. This means that agents work independently and update the model without waiting for others. This approach allows for faster exploration and learning, but it can sometimes result in stale gradients because some agents may be using outdated model parameters when updating. On the other hand, A2C uses synchronous updates. All agents collect experiences and then update the global model at the same time. This avoids the issue of stale gradients since everyone updates the model using the same information. However, it requires all agents to finish their exploration before any updates are made, which can slow down the process. The second, data transmission. In A3C, agents typically send the gradients they've calculated based on their experiences to the global model for updates. In A2C, instead of sending gradients directly, agents transmit their experiences to a central learner. This learner computes the gradients and updates the model accordingly. This method allows A2C to handle larger batch sizes, making it more efficient, especially when using GPU acceleration. The third, architecture and efficiency. In A3C is optimized for CPU environments, where it can run multiple threads in parallel and make use of shared memory without locking mechanisms. This makes it a great fit for environments that benefit from parallel exploration and don't require GPU acceleration. In A2C is more efficient when using GPUs because it can handle larger batch sizes, making it better suited for environments where GPU resources can be leveraged for faster computation. The fourth, exploration and convergence. In A3C offers faster exploration due to its asynchronous nature, allowing different agents to explore the environment in parallel. This can lead to faster convergence, particularly in more complex environments. In A2C with its synchronous updates tends to offer more stable and consistent updates. While it may not explore the environment as quickly as A3C, it ensures that all agents contribute to a single unified update step, leading to smoother and more reliable learning. In summary, A3C is ideal for environments where asynchronous parallel exploration is beneficial and CPU power is available. A2C is better suited for situations where synchronous updates and large batch sizes, with GPU acceleration, are more advantageous. Both algorithms have their strengths, depending on the specific environment and resources available. Now, let's break down how the actor-critic architecture in A3C improves learning. The first, Actor Policy Network. The actor network is responsible for learning the policy, which essentially decides what actions the agent should take in any given state. The actor outputs a probability distribution over possible actions, guiding the agent's decisions based on the feedback it receives from the environment. The actor updates its policy using the advantage function. This function helps the actor understand which actions are better than others by comparing the rewards of actions to the average reward in a given state, guiding the actor towards actions that are more likely to lead to higher rewards. The second, Critic Value Network. The critic network estimates the value function, which tells us how good it is to be in a specific state. This helps the agent understand how beneficial its current state is, which in turn helps evaluate the actions it has taken. The critic also computes the advantage function. The advantage function looks at how much better or worse an action is compared to the average action in a particular state. This helps the agent determine which actions to favor in the future. The third, Advantage Learning. A key feature of A3C is its use of the advantage function to reduce variance in the policy updates. Rather than updating the policy with every small fluctuation, the advantage function helps smooth out the learning process by focusing updates on actions that clearly improve performance. This leads to more stable learning over time. The advantage function also helps balance exploration and exploitation. The actor is encouraged to explore by trying actions that are better than the average, exploration, while also leveraging known strategies that lead to higher rewards, exploitation. This balance is crucial for learning efficiently in a complex environment. The fourth, Parallel Exploration. A3C uses multiple agents exploring different parts of the environment in parallel. This parallel exploration allows the system to gather diverse experiences, which significantly improves the efficiency of learning and helps the model generalize better to different situations. The global model is updated asynchronously by the agents, meaning that they share their experiences with each other periodically. This ensures that all agents benefit from the collective knowledge and learn from the best strategies discovered by others. In summary, the actor-critic architecture in A3C improves learning by combining the strengths of policy learning and value function estimation. By leveraging the advantage function, A3C ensures stable policy updates, balances exploration and exploitation, and uses parallel exploration to speed up learning in complex environments.